Okay, folks, it's time for the next online lecture. Today, we're going to talk about two things. We're going to derive the Poynting vector, and we're going to talk about momentum density for electromagnetic fields. And the Poynting vector involves energy flux of electromagnetic fields. Both of these there's a lot of math to derive both of these results, the Poynting vector and the momentum density of an electromagnetic field. But don't be put off by that, because the results that we get in the end are very simple and very beautiful and even a little bit intuitive. And so you'll have to bear with me on the math, but it's the end result that is most important. But it's nice. But I think it's important also to see how these results are derived. Okay, so let's just remind ourselves a little bit about what happened before. And so what we've been talking about is some of the things that we've talked about before is that if we have a charge distribution, if we have some charge distribution, I'll call it rho of r, then we know that to set up that charge distribution, it takes an amount of energy associated with that. The energy is, we've derived this, the energy, and we can think of the energy as the work that it takes to create that charge distribution, and that work is, we can think of it as sitting in the electric field. And so if we integrate over all volume of the electric field, E squared over d tau, where d tau is the volume element, and that's the energy that it takes to create this charge distribution. And in the last lecture, we similarly talked about a current distribution, and we talked about how much energy it takes to set up a distribution of currents, which is described by a current density, J of R. And we derived that, and we saw that the energy to set up that current distribution, I can think of that energy as the work it takes to set up that current distribution, and that work is living in the magnetic field. So there's a beautiful little symmetry there. It's 1 over 2 mu naught b squared d tau. And so we then can see that the electromagnetic energy we can think of as being stored in both the electric field and the B field. And so we can think of the total electromagnetic field in some region of space, I'll call it U, in some region of space is equal to 1/2 times this integral of these, it's these energy densities. I got the electric field energy density plus the magnetic field energy density, and I integrate them over volume, and that gives me the total energy in some region of space, the total electromagnetic energy. So the thing to think about is that I just want to understand intuitively that fields are equivalent to energy. Energy is stored in electromagnetic fields. Okay, and so now that begs the question: can we, if the energy is in the field, can we move the energy around through the fields? So how does energy move around? How does energy flow through fields, through electromagnetic fields? How do I keep track of the energy? How can I think of the energy as it's moving in these electromagnetic fields? Because energy we can gain energy, we can lose energy, and how do we keep track of all the energy when we have these fields now happening as well? So that's the question that we want to answer, and the answer, of course, is the Poynting vector. That this will lead us to the concept of the Poynting vector. Poynting vector. And so the picture that you should have in your mind, so to derive this concept, the picture you should have in your mind is, let's consider some region of space where there's an electric field and there just happens to be some magnetic field. And these fields have to satisfy Maxwell's equations, which we talked about, which we know. And of course, there might be some charge density in space, rho. I'll call that rho of r. And so if I think of a little chunk of this rho of r, then I can call that dq. A little chunk of this charge density is dq, and that is simply rho of r times d tau, a little volume element. So this is the situation. We have an electric field, some electric field, vector field. We have a magnetic vector field, and we have some charge density. And so let's talk about energy now. So you know that if the charge is in the electric field, then if the charge moves, then work is done. If charge moves, then some work is done on the charge. And so let's ask ourselves, what is the work done on the charge? Work performed, this is how to think about it. What is the work performed on the charge, delta Q, by the fields, the electromagnetic fields? Let's ask ourselves that question. By the electromagnetic fields, what is that work? And then let's take a close look at that expression. So we know there's nothing tricky here. We know that if I have a chunk of delta Q, so if delta Q moves a little distance in the fields, moves by some tiny distance, dl, then I know that the work done on that charge, on that delta Q, is this. It's a little bit of work because I only moved a little bit of distance, and it's going to be equal to the force on that charge. The force that's acting on that charge times dotted into the distance that the charge has traveled. That's a formula that you guys all know well. But what is the force? Well, the force is due to the electromagnetic fields. And so that force is delta Q times the electromagnetic fields. I got an electric field plus I have a magnetic field. And so I have my electric field force and I have my Lorentz force. And so let's just plug it in here, and then we see that the work done on that little bit of charge is going to be delta Q times, now let's plug that in, and I'm going to get two pieces. I'm going to get E dot dl plus, I'm going to get the V cross B dot dl. Right? But now let's remember that the distance I travel, dl, is equal to my velocity times a little bit of time, however long it takes me to travel that distance. So so I travel a little distance dl in a time dt, going at some speed v. So then I can replace these things, and I can say that the work done on that little bit of charge, now over a little bit of time, dt, I can think of that as delta Q times E dot, now V dt, so that's the velocity that the little charge is traveling, plus V cross B dotted into V dt. But now when we look at this expression, we notice that this expression is, you guessed it, 0. And the reason it's 0 is because, just looking at it, it's obviously 0 because V cross B is a vector perpendicular to V, and so that vector dotted into V is 0. But it also makes sense because B fields push perpendicular to motion. The B field pushes perpendicular to dl, the motion, and so it cannot do work. So B field cannot do, oops, wrong do, cannot do work. All right, so that tells us then that the work done, so this is looking really simple. I told you that it'd be hard, and so far it's really simple. So this is telling us that the work done on a little bit of charge that's moving at some velocity in an electric field is, and there's a B field too, is, but the B field doesn't do work, is E dot V dt. A nice simple little formula. And what we can do then is we can replace our delta Q, our little bit of charge. We know that that's equal to the charge density times a little bit of volume, because we're just talking about that little bit of that little bit of charge. And so I can then think of this as the work done on that charge is, and what I can also do while we're at it, we might as well divide both sides by the time, d tau. And so now I can do this. I can think of the work done on the charge per time is equal to, and then I have this, E, and the dq, I'm going to write it like this. I'm going to write it as rho of r times, let's see, rho of r dotted into, let's see the best way to write this. Let me write it differently. I'm going to write it like E dot, oops, and now I'm going to write the rho of r here times the velocity times, and now it's d tau, because that's the volume element that came from this. Okay, I just plugged that in, and so we get this expression. But now we notice something nice. We notice that this is equal to, that this expression is equal to current density, J of r. That's the definition of current density. It's the charge density times the velocity of the charge density, assuming the charge density is moving. And so then we get this expression that the work per time performed on the charge density is equal to E dot J d tau. And so that's the work performed on the moving current density in some small volume. And that kind of makes sense. This should remind you of this thing, V. You guys know that power equals voltage times current. So this should look kind of familiar, because dW dt is power, and E is kind of like voltage, and J is kind of like current. So power equals V times I. It's basically the same expression. And so what we can do then is we can now look for the whole, we can now integrate for the whole system, for the whole charge distribution, and we can integrate over the whole charge distribution, and then we can see the total amount of work, dW total. So the work being done on the entire charge distribution, to get that, I just have to integrate. So I'm just going to now integrate this expression over the volume of the charge distribution, and it'll be the integral of E dot J d tau. And so that's the total amount of work being done. I'll write that here. That's the work. Well, it's the work per time equals power being exerted on the charge distribution. So it's the work. It's the power being given to the charge distribution. Maybe I should use that word, given. Okay, and so I think that's a fairly intuitive expression, and that was sort of the straightforward part. But now what we're going to do is we want to understand better what is the effect on the fields. What is the effect on the fields? And to understand that question, the idea that in your mind you should be thinking that the charge is moving. Charge is moving, and so what is the effect? Charge is moving, work is being done. The charge is moving in the fields, and so work is being done. Then what is the effect of this work on the fields themselves? And that might seem like a philosophical question, but it is not philosophical, because the charge and the fields are intimately linked. How are they linked? Well, they're linked by Ampere's law, and by Maxwell's equations, basically. And so Ampere's law tells us that if we have some current, then we know that it's going to create curl in my magnetic field. And so here's my current, mu naught J. So if physical charge is moving, and I'll call that physical charge that is moving, then I know that is going to create curl in my B field. But I also know something else. This is what we derived last time. We know that that's not the only thing that can cause my B field to curl. Also, my B field will curl if if my electric field is changing. So that's the displacement current. So this I'll call that's the displacement current that we derived last time. Displacement current. And so then what I can see is that I can write the physical current in terms of the fields, and that's kind of a freaky thing, it's sort of freaky to think about, but mathematically it's very simple, because if I start with Ampere's law, then I can see that I can just solve for J, because I see that J, the physical current, the charges that are actually moving, whether it be bound charge, dipolar charge, it doesn't matter. It's all physical charge. The physical charge that's moving, I can write it as 1 over mu naught times del cross B minus epsilon naught dE dt. And I get this just from Ampere's law, just by pulling this guy over to the other side and dividing by mu naught. So this is basically just a way to rewrite. This is still Ampere's law. And so we see that we can write J, the physical charge that's moving, completely in terms of the fields. And so this is how we can figure out what is the effect on the fields of the charge moving, just by making this substitution. So I will now substitute this into this expression. So let's plug it in. And now is when the math gets a little more complicated, because now I can see that the power exerted, the power being acted on the charge, or given to the charge as it moves, is equal to now the integral over the charge density times E dot, and now I will plug this thing in, and E dot J, but now J is, I'm going to rewrite it as 1 over mu naught del cross B minus epsilon naught dE dt. And so so this is another way of writing the power acting on the work per time acting on the charge density. And what I'm going to do now is what we'll do now is what I want to do is I want to get rid of this. Let's see, I'm going to rewrite this. So what I have then is let's rewrite this into a slightly different form. So the volume, and I'll just pull out the 1 over mu naught, just so we can see the vector fields more easily. I have E dot del cross B minus epsilon naught E dot dE dt. Okay, and so this is what I have integrated over the volume of the charge density. Okay, so now what we want to do is rewrite this, and so now I'm going to get very mathematical, but there's a reason for this math. It leads to a very profound and beautiful result. So bear with me as we go through a few lines of algebra. So the first thing that we'll do to rewrite this is we want to get rid of this term right here. So let's change this term, and so to do it, we're going to use a vector identity. A vector identity, and this is a vector identity that you guys have seen before. It's on the inside cover of your book. It's just a calculus identity that you've had to derive sometime or another in your homework. Let's use this. It's chain rule, basically. Let's look at the divergence of E cross B. So this is just pure math. And we know from the chain rule of curl and dot product, we know that del dot E cross B, and this is a vector identity, is B dot del cross E minus E dot del cross B. Okay, just a simple little thing. And the thing that we want to get rid of is remember in our integral we have this term, and so now I see it here. So let's solve for that, and I have let's bring it over to the other side and bring this over to the other side, and so now I'm going to have E, whoops, sorry, this stupid thing keeps screwing up. I have E dot del cross B, and it's going to equal it's going to equal B dot del cross E and minus del dot E cross B. Okay, so I'm just using that identity, but then I notice that this thing, this thing here is del cross E. And what's del cross E? Well, I remember that del cross E, curl in the electric field, comes from negative dB dt. And that's just Faraday's law that we derived previously. And so we see that that curl in my electric field can come from a changing magnetic field. So I can make that change, and so then I see that this is equal to negative B dB dt minus del dot E cross B. So this is the thing that we want to get rid of here, this guy, and we now can write it in terms of this. So now let's plug this in here, and so now we can see that, so now we have a new integral. We see that the power, the work per time being exerted, the work being done on the charge distribution can now be written as a volume integral of all this stuff. So I plug it in. It looks more complicated, but we'll be able to simplify it soon. But now let me plug it in. It's going to be minus 1 over mu naught B times dB dt minus 1 over mu naught times del dot E cross B. And that's just coming from this, so it should look familiar. But now I have that last term, which is minus epsilon naught E dE dt E times dE dt. And this whole thing is integrated over volume. Okay, so it's looking kind of complicated, but something very beautiful is about to happen, because what we notice is that look at these two terms. This term here and this term here. There's something very interesting about those terms, because check this out. This is a very cute math trick. If I have B dot dB dt, then I know that that is equal to 1/2 times d dt of b squared, because of chain rule. So just do it and see. They're equal. And by the same token, I see that E dE dt is of course equal to 1/2 d dt e squared. And so what we can do then is we can plug this in here, and we can plug this guy in here, and then that allows us to rewrite this stuff like this. We can now write this integral, the power, the work per time that's done on the charge distribution by the electromagnetic fields, is now I can write it in terms of these time derivatives. So I take that time derivative and I can pull it out, and it's going to be negative d dt of this, and I have those 1/2s, the little 1/2 factors. So I'm going to have times 1/2 epsilon naught e squared plus 1 over mu naught b squared. So I got that. And so I'm going to break it up now into two integrals, d tau. But now I got this other term here too. Oh no, not that one. It's this one, I'm sorry. This term. Let's erase that. And I got that last term, which right here, which is minus 1 over mu naught integral of del dot E cross B. Integrate over volume. Okay. And now let's do something else. Let's do two things. Let's take this. We'll take this time derivative outside of the integral, but we're also going to do something here, because we notice that this is the integral over volume of a divergence. And so we're going to use you guessed it, the divergence theorem. Divergence theorem is what we always like to do in E&M. We're going to turn this into an integral of, we know that the integral of del dot something d tau is equal to the something dot dA. So we're going to go from a volume integral to a surface integral. So that allows us to then rewrite the work per time exerted on the charge distribution by the electromagnetic field. Looks like this. We have two parts: a time derivative of this integral, the integral of 1/2 times epsilon naught e squared plus 1 over mu naught b squared d tau minus 1 over mu naught, and we'll do the divergence theorem, this integral over the surface bounding the volume. So this one is over a volume, and the second integral is over the surface bounding the volume of E cross B dot dA. Okay, that is the result. And let me just put a box around it before discussing it. That is the result. And this is called Poynting's theorem. Oh, shit. What was that? What the hell happened there? That was unfortunate. I don't know why that happened. Let me do it again. Maybe I'll not touch it there. So that's the box, and so this is Poynting's. Jesus Christ. I hate when the thing thinks it's smarter than you are. So this is Poynting's theorem. And it's very important. And I want you to take a look at it because there's something really interesting here. Because first, I want you to take a look at it. Might just seem like if you've never seen it before, it might just look really crazy to you. But first, take a look at this. What is this expression here? That expression is the electromagnetic energy density, which I just mentioned at the very beginning of this lecture. So if I have an electromagnetic field, then the energy per volume is this expression. It goes as E squared plus B squared. And so you can see that this volume here, this volume is the electromagnetic energy, the electromagnetic field energy. It's the energy in the electromagnetic field in that volume. And we were talking about the volume of the charge distribution, but now we've through all this mathematics, I've sort of changed it to being, I see that when I'm talking about the work per time performed on a charge distribution in some volume, and I can see that work per time can be written in terms of a time rate of change of the electromagnetic field energy in that same volume, minus this surface integral over that volume of this weird, I didn't write that, of this weird vector E cross B. And so let's rewrite that. And what I'm going to do is let's define a vector. We're going to define the Poynting vector. Define the Poynting vector. S is equal to 1 over mu naught E cross B. We're going to define that, and it's called the Poynting vector. And it comes from this derivation because it comes from, you can see where I did it because it comes from here. Because I have the 1 over mu naught E cross B. So that's the Poynting vector right there. And so that integral is going to become, let's see, that integral is going to become minus the integral of S dot dA. That was the whole point of defining the Poynting vector. And this electromagnetic energy density, let's call that, so let's rewrite this. So we're going to rewrite this complicated Poynting theorem in a more simple way, because what we're going to do is we're going to say that the total electromagnetic energy, jeez, this thing is really acting up today. The total electromagnetic energy is equal to, if you guys can tell me, if someone can tell me how to turn that off, all these automatic autocorrects that are happening, I really hate them, and I'd like to turn them off, but I don't know how. So if anyone knows how, email me and let me know. But the total electromagnetic energy living in the volume of the charge density is this integral. Oh, see, it did it again. Jesus Christ. It's this integral 1/2 epsilon naught E squared plus 1 over mu naught B squared d tau. So this integral, it's the integral over the volume of the energy density is the total electromagnetic energy energy. So total energy of the electromagnetic fields. It's the field energy in the volume of the charge density. And so making these definitions of the S and the U, I can rewrite the Poynting theorem to look like this. I can rewrite it as what I can do is this is how I like to write it. I'm going to take this part, which is just negative U total, right? And I'm going to pull it over to this side, and I'm going to take this and put it over to the other side. And so I'm going to rewrite that expression in this way. I'm going to write it as d dt, because this is the u inside of the derivative. I'm going to write it as the time rate of change I'm going to write it as the time rate of change of u total is equal to negative dw dt plus negative integral over the surface of s dot dA. And so, and this is the, and that's the total, the time rate of change that's the time rate of change of the electromagnetic energy over the volume. And so this is how I will rewrite this. And what I want you to see is that this is just conservation of energy. I want you to see that this Poynting theorem is just an expression of conservation of energy. And so it's actually, it turns out to be, it's a very intuitive expression, because I want you to see that what we have is we have the change, the time rate of change of this is the change in the electromagnetic field energy in that volume, the change in the electromagnetic field energy. So the way to think about it is that if the electromagnetic field energy U is changing, then ask yourself, where is that energy going? Well, that energy has to go somewhere. And so the first place it can go is into the charge density. This is the change. So this is the power, dw dt is just the change in the energy of the charge density, energy of charge density. And so this is saying that, and so think about it, if the electromagnetic field is losing energy, then the time rate of change is negative, and then and that means that the work done on the charge density is positive, because it's doing positive work. So the energy is going to the charge density. So that makes sense that the du dt would equals negative dw dt. But then there's something else. There's this. And this is a really strange expression, because what we have here, we see that we have power. We ask ourselves, the first expression, du dt, is the energy in the electromagnetic field in the volume. It's changing, and I can see that energy goes into the charge density. But what is this last term? This is a flow of energy out or in, flow of energy into or out of, depending on the details, the region of the charge density. And so this is the really cool thing. What we've derived today is that the energy of the electromagnetic field can, the electromagnetic field can exert energy onto the charge density, but it can also, but the energy can also flow in and out of the region that we're talking about. And so that's a really profound thing, because this is the first time in this class that we've ever really showed that how energy can flow purely by electromagnetic fields. And so that's kind of cool. And so, so we think of S, the Poynting vector, is 1 over mu naught E cross B, and we think of this S as the flow of its, you think of it as energy flux. Energy flux. It represents the flow of energy. And so let me think, maybe pictorially, how can we represent this pictorially? The way to think about it is I have some I have some energy density here with some E and B fields, and then it's acting on some charge density rho of R, and so energy can flow into the charge density, but energy can also flow out of the volume of that region. So energy so the energy can go into the charge density, but it can also flow out by the fields. So this is the energy equals energy flowing out. Or it could flow in, depending on the details. Or in. Okay, so and there'll be more, and the best way to think about this is to sort of do some problems and to sort of play with it yourself. But there's one other thing that we want to point out too is that we see that this flowing of energy, the way we derived this was from a point of view of conservation of energy. But I want to point out that we also, what you might be thinking to yourself, what about, there's another important conservation law, which is conservation of momentum. And so you might ask yourself, so this first one, so the Poynting vector is telling us that the electromagnetic fields carry energy. We already knew that they carried energy, but now we know that the energy can move around too, and that the Poynting vector tells us how the energy flows in an electromagnetic field. But what about momentum? That's something that we haven't talked about yet. We see that electromagnetic fields can carry energy, but can they carry momentum? That's an interesting question. And so let's answer that question. And the way we'll answer that question is very similar. We'll do a very similar derivation to what we just did a moment ago. We'll consider, let's consider some charge density, rho of R, that's living inside of some electromagnetic fields. There could be some B field, some E field. And now we're going to ask, how is momentum conserved? And so to understand how momentum is conserved in this field, in this situation, we have to consider the forces, because momentum is all about force, right? F equals ma. Consider force. Remember, F equals dp dt. So if some force is being pushed on something, then that causes its momentum to change. So force and momentum are intimately linked by this expression that you guys all know and love. So let's consider the force on the charge distribution. And let's see where that takes us. So we know that if I consider some little itty-bitty part of this charge distribution, I'll call that little volume d tau, then I know that in that volume, the force is going to be, there's going to be a little itty bitty force acting on it. So there's a little itty bitty force acting on that little itty bitty volume. So I'll call it dF. And that force is going to be equal to, well, there's two things that can on that little volume. If there's charge density in that little volume, then I know that I'm going to have rho d tau times electric field, because that's the charge, right? dq, delta q. And so I know that the charge times the electric field is a force, but that charge might be moving too. If the charge has some velocity, then I know that I can also write it like this, plus j cross b d tau, where j is rho v, right? So I have the electric field force and the Lorentz force, because the magnetic field can add a force as well. So then what I can do is I can then ask myself, what is the force per volume? And so I can calculate this, this is really a force density. And we can get the force density, and I'll just call it little f, the force density in this volume, little f, is equal to the force acting on that charge divided by the volume. And so that's just equal to this expression, rho times E plus J cross B from above, from this line above. And so we see that the force per volume acting on the charge in this charge density is going to be the rho times E plus J cross B. So that's the force per volume. And so what we want to do now is we can calculate but what we can do now is we can start to manipulate this, and because we want to write this completely in terms of the fields. So we want to write in terms of the fields. In terms of fields. And so to do that, we're going to use the same trick that we did before. And so we're going to use, but plus a new trick actually. So we want to, let's do a trick. Let's get rid of the charge density and the current density. So change to fields. Change to fields. And how do we do that? Well, we know that if we have charge density or current density, then we can write it in terms of electromagnetic field using Maxwell's equations. And so to get the first one, we'll just write, we know that if there's some charge density, then there's got to be divergence in the electric field, because they are the same thing. Charge density is equal to epsilon naught times divergence in the electric field. And similarly, we know that if I have some current density, then I can write that in terms of curl in the B field minus epsilon naught dE dt. And this is the same thing that we just did this a few minutes ago. This comes from Ampere's law, remember? Del cross B is equal to mu naught J plus mu naught epsilon naught dE dt. So from Ampere's law, I know that if I have current, then I must have curl in my B field, but also I can write that in, but I also might have some changing electric field too. So this is the expression for so I can use these expressions for current and charge density, and then I can plug them into this. And so then I see that my force per volume, my force density on the matter. This is the force per volume on the charge density, on charge density. Don't forget what it is equal to, and now I will plug those things in. It's equal to epsilon naught times del dot E times E plus J is now 1 over mu naught del cross B cross B let's see, I'll write it like this, minus J is, let's get all these, minus epsilon naught dE dt cross B. Okay, and so let's rewrite this as FV, the force per volume, is equal to epsilon naught del dot E times E plus, and now let's break this up into pieces, 1 over mu naught del cross B cross B minus epsilon naught dE dt cross B. Okay, so we've basically taken a simple expression and made it more complicated with some math, but there's a reason why we did it. It's because we want to relate the force we want to relate the momentum of the charge density to the momentum of the electromagnetic field. That's the whole point. We haven't gotten there yet, but that's why we're doing this. Okay, so we have these three terms. I'll put double underline on them. And so now we're going to manipulate this expression some more. And the way we're going to do it is we're going to do sort of a real tricky thing, something that you would never think of doing unless you're like a really smart, really brilliant math person. What we're going to do is we're going to we're going to do the old add zero trick. Add zero trick. We're going to use the add zero trick because you know that if I have some equation, something equals something, then I can always add zero to it. If something equals something, I could say something equals something plus zero. That's also true. So I'm going to do the old add zero trick, which is, I'm sure you've all seen it somewhere before. So what I'm going to do is I'm going to add zero to this right hand side here. I'm going to add zero to that side, but it's not just any zero. I'm going to add a really weird zero. 0 equals, and let's look at this, negative epsilon naught E cross dB dt, and there's a reason, of course, why we do this, plus epsilon naught E cross dB dt plus 1 over mu naught B times del dot B. So this is a very inspired choice of zero. And you can see that it's zero because, look, del dot B is equal to 0. And here I have minus of something, and here I have plus of that same thing. So these two guys together equal 0. So I see that this expression certainly does equal 0. So now I'm going to take this expression and I'm going to add it to, to this expression here. And so what I'm going to do is I'm going to write it like this. F of V, the force per volume on the charge density is equal to, and so now I'm going to write it like this. It's equal to negative epsilon naught dE dt cross B And so I'm going to do a double underline because that's my old expression. That's this term here from my old expression. But now I'm going to add that 0, part of the 0, minus epsilon naught E cross dB dt. That's part of the 0. Let's get rid of this. Plus epsilon naught del dot E times E. And that's from my original expression. That's not part of the 0. But then I'm going to go plus 1 over mu naught del cross B times cross B. That's part of my original expression also. But now I'm going to add those other 0 terms, which is going to be minus epsilon naught E cross del cross E plus 1 over mu naught B times del dot B. Okay, so why did I do that? Well, the reason I did that, the first reason is because, so that's my force per volume, and the underlined parts are the original parts, and the parts that are not underlined add up to 0. And the reason I did it, I write it like this, is because I want you to see that this is sort of the most important part there, because you see that's the time rate of change of E cross B. So what I can do then is I can take that and pull it over to the other side. Oops. I can pull it over to the other side, and I'm going to write it like this. I'm going to say FV, the force per volume, plus epsilon naught d dt E cross B is equal to all that other stuff. Epsilon naught times E times del dot E minus E times cross del cross E plus 1 over mu naught times B times del dot B minus B cross del cross B. And we write it, I write it like this so you can sort of see the symmetry of this expression. So this is what we've derived. And so what I'm going to do is I'm going to take this. So this part is the really nice part, and we'll talk about that in a few moments. But this part is the ugly part. So this kind of ugly part, let's give it a name. Let's just call this. It's a vector. It's a vector field. Obviously, it's a vector. We'll give it, and so we'll call it G, the vector field G. And so it's complicated, but you can see how it has this symmetric structure to it. And so what we can do is, and so now I'm gonna skip some steps, because to do this correctly, there's a lot more math, and so I want to simplify it. So I want you to take it on faith, and maybe even you can kind of even see it, but let's assume that G, let's make an assumption that G is equal to, let's make an assumption that G, let's make an assumption that G is equal to del dot chi. Now, remember, if I have a vector field, normally del dot a vector is the divergence, and that's a scalar. But I have here a vector, and so this, if this is a vector field, then that means that this has to be a tensor. basically a matrix, 3 by 3 matrix. And this is true because I can construct a matrix such that if I take the divergence of that matrix, the divergence of that matrix is equal to this expression, G. I can do that. But the problem is that I'll write it here. I'll say G equals del dot chi for some chi. And I'm not going to derive chi, because to derive it is a lot of algebra, and it's sort of not worth it for today's lecture. And so chi is pretty messy. It's pretty messy. It's big and ugly. And it's a tensor. And it has a name. It's called the Maxwell stress tensor. Maxwell stress tensor. And the reason I'm not actually writing it out for you is because, and I want you to see that it's equal to, it's some very complicated expression of involving the E and B field. Now, the reason I'm not writing it out is because when I was an undergrad, my professor derived it, and we did it all in detail. And also when I was a graduate student, we did it again. And I just want to say that in the last 35 years, since I was an undergraduate, I have never once used the Maxwell stress tensor. I have never used it even once. I've never even seen it used. Now, that doesn't mean it's not used. I mean, for some other people, it might be the most important thing. But for me, it is not. I have never used it even once or seen it used in 35 years. And so as a result, I'm just not going to bother deriving it. But it's important that you guys know that it exists. And so what I will do is we will just assume that there is an expression for it. And so that means that if we assume that it exists, and so we can write that the force per volume acting on a charge density living inside of some electromagnetic field environment, that force per volume plus this expression, epsilon naught times d dt of E cross B is equal to del dot chi. Okay, so we will just write it like that. We will just replace this big ugly expression with the simpler del dot chi. Okay, and so this is important because now what we're going to do is integrate. We're going to integrate over all space. Let's integrate over all space. And so I'm going to do this. We're going to integrate this volume FV, the force per volume, plus this other little extra part, this time derivative, E cross B, d tau. We'll integrate that over all space. It's a volume integral. That means if we do the left side, we got to do the same thing to the right side to keep it as an equation. So we're going to integrate this volume over del dot chi d tau. But now you can see something very cute happens because now we're going to use, we have an integral of a divergence. So let's use the divergence theorem. And this is just a multi-dimensional generalization of the divergence theorem. But if I have this, but you can show that it's true pretty easily. If I take the divergence of this tensor over some volume, then that has to be equal to the integral over the surface that bounds that volume of chi dot dA. And you can't do that because this is a matrix. You can always dot a matrix into a vector. That leaves you with a vector. And so I can do this, but then what we can do is if we integrate over all space, then that means that the volume goes to infinity and the surface goes to infinity. And what is the value of E and B at infinity? Well, we know that. E and B go to 0 at infinity. And so that means that the Maxwell stress tensor goes to 0 at infinity. And so infinity is a very stress-free place, unlike where we are now. And so that means then that I can write this. I have this expression, which is that all space, if I do the integral over all space, fv plus epsilon naught d dt e cross b d tau, then that integral over all space is 0. And so that's a pretty beautiful result. So there's lots of math, lots of complexity, but it sort of ended up being this very simple expression. But let's keep going. Let's go a little further. Because remember, the whole point is that I have some charge distribution, and so and F is the force per volume on that charge distribution. So if I integrate it over all space, then that means that, remember, the integral of F of V over all space has to be the total force on my matter, the total force on the matter, the stuff, which is equal to the matter is the charge density. That's what matter is. That's what stuff is. That's what me and you are. We're charge density. It's just walking around, charge density. Okay, so the matter is so this integral is the force on the stuff, the charge density. But then I have this other integral, but I don't forget this. I got to integrate that too. What the hell is that? So let's rewrite this. So what I can do is I can write this as force total on the matter, and maybe I'll write it, instead of saying force total, I'll write it like this. I'll say the force on the matter, M for matter, or maybe I'll just spell it out. The force on the matter plus, and then I'll do this, dt, and this now is going to be, I can take the integral, I can take the derivative out of the integral, so I can write that as ddt of this, the integral over all space of epsilon naught e cross b d tau, and I see that now this whole quantity is 0. Okay, that's interesting. It's starting to look sort of familiar. I got a force, I got a time derivative. It's starting to look a little bit familiar, but let's keep working on it. Now, if this is the force, let's go a little further. If this is the force on all the matter, then that means that is got to be equal to the time rate of change of, you guessed it, the momentum of all the matter, the stuff, the momentum of the charge, because like atoms and electrons and nuclei flying through space. So this force on the matter is equal to the time rate of change of the momentum of the matter. And this is all the matter in my little universe that I've integrated over. And then that's plus ddt of this stuff is equal to 0. And so then what I can do is I can simply take the time derivative out, and I can write that this equation is the time derivative of this p matter plus that integral, the integral over all space of, I should have written it in here, this also was going to be the integral of all that stuff. The integral over all space of epsilon naught E cross B d tau equals 0. Okay, this is where we wanted to go. So what I have now is the time rate of change of momentum plus something else equals 0. Now, okay, what the hell is this something else? Because normally you would have thought that I would just say d dt of p of all the time rate of change of all the matter in my little universe is equal to 0. That's what you would have thought, because momentum is conserved. And if I have all my material in my little universe, then I should have this, right? d dt of p matter equals 0 for the whole universe, in my little pocket universe. But this is not true, because this is ignoring the fields, ignores the electromagnetic fields. And the electromagnetic fields carry momentum. So the electromagnetic fields carry momentum. And what is the momentum that they carry? Well, we know that they carry this momentum, that this thing has to be the momentum that they carry. This stuff has to be the momentum of the electromagnetic fields. That's the missing part, because I have the time rate of change of the momentum of the material plus some other thing equals 0. Well, what the heck is that other thing? It's got to be the momentum of the electromagnetic field, because now I can say d dt of, it has units of momentum, it has to, of the momentum of the matter plus the momentum of the fields equals 0. And so what we've just derived is that basically we've just derived that electromagnetic fields have momentum, because the thing is, if the time rate of change of these two things is 0, then that means that if this goes up, then this goes down, and vice versa. It means that if my material is sitting in an electromagnetic field and it moves, basically this is my electromagnetic field and this is my charge. If my charge starts moving the electromagnetic field, then what happens is the Q momentum goes up, but the electromagnetic momentum has to go down. Goes down. So if I keep track of all the charge and if I keep track of all the electromagnetic fields, then when the momentum of the material goes up, the momentum of the fields goes down, or if the momentum of the matter goes down, the momentum of the fields goes up. So there's a conservation there, and the electromagnetic momentum can be written as an integral over volume of epsilon naught E cross B d tau. And that's the big result here. And that is very significant. And so so what we can see then is that this expression inside, since it's integrated over volume, that must be the momentum density. Momentum density of the electromagnetic fields. And so I can write it like this: G equals, I'll call G the momentum per volume, the momentum density of the electromagnetic field, and G is equal to epsilon naught E cross B. And I will also mention that we could also have the electromagnetic field also has angular momentum. I'm not going to derive that, but it sort of is very general. It's generalizable. Also, it also has angular momentum, and that's actually pretty easy to see because you know that angular momentum L is equal to R cross P in classical mechanics. And so if I have some angular momentum density, G, if I have some momentum density G, then I can see that my angular momentum density is going to be equal to R cross G. Because if L equals R cross P, that's the angular momentum, then L equals R cross G must be my angular momentum density of the electromagnetic field. So electromagnetic fields carry momentum. That's the big thing. They carry energy and they carry momentum. But it's not a flow of momentum, it's just a momentum density. So today, I just want to be clear, today we derived that S is equal to 1 over mu naught is equal E cross B is equal to an energy flux. That's the energy flux. And it's a flux in all the meaning of the word flux. I mean, it's equal to I can write that as an energy density times a velocity if I want. It's a flux. It's the movement. That's what we derived before, that the energy flux carried by the electromagnetic fields is S. That's the Poynting vector. But then what we also derived is that that electromagnetic fields have a momentum density. G is equal to epsilon naught E cross B. And this is a momentum density. So they're different. I just want to emphasize that they're different. Momentum density. It's not a flux. We're not talking about a flow of momentum. We're talking about just the electromagnetic field is sitting there and it just has momentum. It just carries momentum. And this point is sort of trivial in one sense, but kind of confusing in another sense. And it is also a little funky because you can see how you can write one in terms of the other. You know, you can say, for example, I could say that G is equal to mu naught epsilon naught S. So you can sort of see how you can write one in terms of the other. But that's a little bit confusing because they are different things, okay? I have a momentum density is G and S is an energy flux. Okay, folks, I think that's a good place to stop. I'll see you later.